Okay, so we'll get started. My name is Jared Beaton. I'm one of the earth science professors here on campus. And I would like to introduce two of our very excellent senior level earth science majors. They've been doing this research for about 3 years. So I'm going to turn it over to them to tell you all about it. Please welcome Dan Carver and Gary Potter.
Well, thank you all for coming, and I hope you enjoy the talk to come. We're going to be speaking about determining the age of dirt. It's kind of a light title for a little bit of a more general talk than what we've been giving in the past. So Gary and I are both Porter Scholars, and we actually received funding from the Porter Scholar Focused Academic Fund to get money to date organic material in soil horizons as part of our senior capstone project. So this kind of ties in the project we've been working on, and then also the what's new to it this year. So we'll get to, right here you can see this little dark band. It's actually a layer of charcoal. That's something that you would look for when you're dating soil. And then this is a character we'll talk about soon enough. Okay, so we're geographers. Big thing about geography is there's always a map. It's where you start with any project. And it shows our research area. We have 7 different study areas at this point. These are locations on these rivers with a defined section of soil. And then we're really looking at Lahara Creek, Ha Creek, and the Alamosa River. These are southwest of town. If you guys ever want a cool place to go, they're very nice. But like Dr. Beaton said, this started in 2009. We, as of so far, have described 21 soil profiles. We've done a lot of laboratory analysis on it, and then mapping to go along with it. So it's a big project that has developed over the years. So I'll run through a quick outline of what we're going to be speaking about today in the presentation. Gary's going to start us off with just a little bit of background on soil. People may be unfamiliar with it, so it's good to have some information to start with. Then we're going to go on to, in my opinion, what are the fundamental questions of earth science and how they relate to this project. And then the almost laws of earth science. If you've ever talked in earth science or asked them a question, almost comes up a lot, or maybe, or sometimes. So we can't really have laws, it seems like. Our married man over here is going to talk about advanced dating techniques. And then we're going to tie this all back into our project and talk about how old our dirt is. And then the final kind of conclusive idea of this archaeological prediction model. So with that, I'll turn it over to Gary.
Okay, so what is a soil? A soil incorporates the 4 spheres of earth science: the lithosphere, the hydrosphere, the biosphere, and the atmosphere. What this means is soil is a dynamic composition of mineral matter, organic matter, water, and air. These different factors are determined by, or can be summarized by the acronym CORPS. So these 5 factors affect how a soil is formed. So climate, organic matter, relief, parent material, and time. So what this means is that any soil that is formed in the same climate, has the same organic matter, has the same relief, the same parent material, and is formed at the same time, is indeed the same soil. But if any one of these factors is different between 2 soils, then they are different soils. An important thing to note here is soil is an indicator of a stable landscape. So what this means is that a landscape has to be stable. It cannot be either grading or degrading to be stable and for soil to start formation. And organic matter in a soil can be dated. So here's 2 different pictures. And this one down here, it's really hard to see. There's this band right here. It's kind of darker. I'm not sure if you guys can see that or not. But that would be an organic rich surface horizon that used to look probably something like this top image. And then aggradation occurred, so buildup of sediment occurred on top of that. And so now we can go and we can take the organic material from this band, date it, and then we can say about how long ago that aggradation started to occur. Back to Dan for earth science.
Yeah. So I've been studying earth science for 5 years, and I've kind of made some conclusions about what we do, and summed it into 3 questions. And the first question we ask is, what is that? When we're outside, when we're looking at stuff, that's our first thing that comes to mind. What is that landform? What is that feature? And it's this encompasses how we collect information. So by asking this question, we go out, we make observations, we collect material to bring back to run test-ons to figure out what that landform is. The second question, which is the majority of earth science, I think, is how did it get there? Once you identify a feature, you can kind of try to explain the process behind what was happening to make that feature become part of that landscape. And this is what the majority of what we've done within our project, as well as other projects in earth science, is the process behind what's happening. And the third question is, how old is it? We're going to be talking about ways to determine that throughout the rest of the talk. So we'll move on. Has anyone heard of this before, principle of superposition? If you've taken a geology class, I see Lyle back there nodding, yeah. This is a big part of what we do in geology as well as geography. So the big idea of it is which one was there first. In this case, I'm providing a modern analog to this scientific principle to say that the car, this lower layer, had to be there for another layer to be deposited on top of it. Fairly straightforward, but has a lot of strong implications within earth science. So we can say the material on the top is the youngest. We see this here in the soil profile. We have this oxidized layering down here, which is older than this darker layer on top. And then in geology, we'll see that as well. You have a white colored sandstone below, so it's older, and a red colored sandstone on top, and that's a younger material. The next one, the principle of cross-cutting relationships. So this is a picture of a screen door and a dog nose. And I think it's kind of obvious which one was there first. The screen door had to be there for the dog to run through it. Simple as that. And what this principle tells us is that material intruding through an existing medium is younger. So we'll use this in soil science. It's a little difficult to see, but you can see these round features here. These are called crotovinas. These are animal burrows that have been dug through the material and then filled in with younger material from the top. So you have this intruded layer of young material within an older sediment package. This is probably the number one source of relative age dating for geology as well. We talk about igneous intrusions, faults, all these movements of rocks that really get related to cross-cutting relationships a lot of the time. And the third one is culture deposits. So for this, let's say you're starting to clean your room and you're reaching way back under your bed and you find this box and you have no idea what's in this box. It's dusty, you just have no clue where it came from. And you open the box and you find this. Jody Mitcher's Jazzercise poster, actually. So this is a piece of a culture that's really identifiable to a select time period. People today aren't putting this on their wall. So this is obviously from the past. So what this tells you is that items found in place can be identified to belong to a specific culture and can be used to date that medium. In our areas, we find this a lot with archaeological materials. This is a stone tool made from the Cumbres chert, and it was used extensively by the Folsom culture, which is up to 10,000 years before present. So if we found this material, this is on the surface, so it doesn't tell us anything about the medium. But if you found this buried within a profile, it can tell you that it was up to 10,000 years ago that that material was dropped. So that profile is up to 10,000 years old as well. By and far, what we do the most of is comparison. So we take two different soil profiles on the same landscape and look at them. We look at a lot of different factors of these profiles. The geographic position, where these profiles are relative to each other. The geomorphic position, are they sitting higher than one another on the landscape? A soil profile, the soil consists of different horizons that we can describe and identify. We can look at the color of those horizons. Colors tend to redden with age, so it tells you something about the age of the material. The structure, again, another feature of a soil that will develop over time. You can use to identify relatively the time boundaries, percent organic matter of these horizons, as well as texture, which is how much sand, silt, and clay are in the profiles. So we compile all this information in charts and tables and things of the like, so we can visually compare them next to each other to try to get an idea of how old these materials are. Are they the same profile? Are they different? They're the questions we ask for relative age dating techniques. By the comparison method, these two profiles at Hawk Creek, these T2 surfaces, we believed were the same profile, the same age. Okay, turn it over to Gary.
Okay, so before we get started with our advanced dating techniques, we'd like to thank this guy right here. This is Dr. Hong Wang from the Illinois State Geologic Survey. He's the guy that we've been sending all of our material to get radiocarbon dating done. So we asked him once if we could get a date off of a 0.15 gram piece of charcoal, and he replied to us with some confidence that I can get 10 AMS dates off of that. So just a little bit of history. In 1992, you could not get an AMS date off of a 1.5 gram piece of charcoal. So this just shows how the technology has really advanced in the last couple of years, and you really only need a really, really tiny piece of charcoal to date. So we'll go into collection methods. So basically what we do is we go out in the field and we describe these profiles, and when you start collecting for radiocarbon samples, though, you have to figure out what you're going to date and why you're going to date it. So why is that important to what you're researching? So often what Dan and I have done is collected material from a buried surface A horizon, which means that at some point in the past that was the surface of the landscape, and it has collected a lot of organic material. That organic material can be dated, so that's why we look for these buried horizons. You really, really can't see it, but in this picture there is a buried horizon, but it all looks black in this picture, so not a very good teller. So then the other thing is that if you want to date something that's not a buried A horizon, something that doesn't have organic rich material, how would you do that? And what we do in that case is you look for a piece of charcoal or a piece of bone or any piece of organic material that has been deposited in that layer, in the layer you're trying to date. So in this case, it's kind of hard to see, but right here is a little piece of charcoal that's stuck in the side of this cut bank. And so you can collect that and date that, and that tells you how long ago that sediment was filling up. I think we have another picture here. Yeah. So this one you can see a little bit better. Right about here is a darkened layer, and that would be buried organic horizon.
Can you point that out again? I couldn't see
The pointer, here, I'll just point it out.
Yeah,
I don't want to get too much in the picture, but it's right through here.
Okay.
There's this dark band. So, yeah, basically then this last picture would be what you would do. We would go out in the field and we collect soil with a shovel with gloves on and put it in this plastic bag. And we collect all the layers, not just the organic ones, so that we can do a sediment profile. And then we collect the organic layer. We take it back to the lab. You have to pull out the modern roots because those can offset your AMS dates. And then you put it in a baggie and send it to Dr. Hong Wang, and he sends us back a numeric age. Says this is how old it is.
You also have to send him a check.
Yeah, that too. So radiocarbon dating. Just a little bit of background on what radiocarbon dating actually is. So radiocarbon dating is determined by a ratio of carbon-12 to carbon-14. So these are isotopes of carbon, and while an organism is alive, they inhale carbon through CO2, both carbon-14 and carbon-12. When an organism dies, the ratio of carbon-14 to carbon-12 starts to change. So carbon-14 is radioactive and carbon-12 isn't. So when the organism dies, the carbon-12 stays the same, and the radioactive carbon-14 starts to decay over time at a known rate. So then you can look at the ratio of carbon-14 compared to the ratio of carbon-12, and you can tell how old something is up to a certain amount of time. So the ages of our dirt. So this is our Hawk Creek locality. This is me after I fell in the river. Again, these pictures, it's really hard to see, but there is a buried organic horizon right here that we're collecting. And that's one of these dates. And then this is just, this other picture on this side is showing the difference between looks like the T1 and the T2. So the older T2 is on the top, and then just further down is the next river surface that was a floodplain at some point. And so what we do is we go out and we collect these soils, and we've got these dates. So this one at Hot Creek, the one Jan was showing earlier, we thought was the same profile, but one of them turned out to be 1,250 years old, further up the stream, and then the same, what we thought was the same buried horizon, downstream further, turned out to be 3,000 years old. So they're both T2 surfaces. We thought they looked exactly the same from all of our analysis that we could do on it, but it turns out that they're different soils because they're different ages. They're formed at different times, it makes them different soils. So it just goes to show how important these dates can be. And now we know that everything above, above this layer at 1,250 is younger than that, and in that particular area. And then in the lower area, it's around the same depth, but it could be older because it's, the date's 3,000 years old on that same, what looks like the same layer. So this is our Alamosa River locality. I don't know if you guys have ever been up to Alamosa River, but this is the runoff of the Summitville mine. So that's why there's all this orange, nasty color in most of this, is because it's all mine drainage runoff. We have 3 dates here. One is a T1 and one's a T2, or 2 are T2s. So one of them is from this piece of charcoal in this picture that I'm pointing to with the ruler. You can't really see it all, but that's the, I believe that's a 3065 date. And then we have another date from a band that's further over, but it's similar to this band right up here. That's this 2150 date. And that can tell us something about how quick, because they're so close together and in the same cut bank, it can tell us something about how fast the profiles are grading right there. And then the T1, which is this surface here, you can't see it, it's this one on this side. We got a piece of charcoal from underneath where that cut bank is. You can kind of see where there's a shadow. There was some charcoal down there, and we dated that so that we could tell the difference between the T1 and the T2. So T2 is an older alluvial landscape, and the T1 is a younger alluvial landscape. So then by knowing that, we can tell approximately how far down, or how quickly the stream was down cutting. And then our last one is this one at Lahara Creek. We got a couple of dates here, all around the same. This newest charcoal one here, the 485 was from a T1, and the other 2 are from T2s. So kind of trying to figure out the same thing we were at the Alamosa River. Turn it over to Dan for talking about predicting modeling a little bit.
So what we haven't done yet is really explain why we're collecting this material, why we're looking at soils, why we're getting these dates. And it really all ties into this idea of a archaeological prediction model. Like Gary mentioned earlier, with the buried soils, they represent an old landscape. So at, let's say, on this is a map of Hot Creek. At 1,250 years ago, there was a surface underneath this blue polygon. So if you're looking for archaeological materials from that age, you can look at that area within Hot Creek. If you're looking for older materials from, let's say, the 3,000 year range, you can look at this blue polygon down here. So this is something we can provide to archaeologists, other people who are interested in going out in the field and looking for stuff, to really try to get a better idea of what dates material was stored in specific locations. Areas that we don't have dates from, what we can say is that they're younger than the material that we have dated. So with some concluding remarks, these numerical ages, it's been a great experience to work with them and to learn the process. The carbon-14 dating is a kind of the accepted way to date material in quaternary sciences. But they're not answers. They're just another piece of data that has to go into your previous work. Those initial 2 questions are still the main focus of any research project, and the dates you kind of have to try to fit into those talks, or into the numbers now. And that's it exactly. The numbers does not explain the process. It doesn't tell you how the material got there. It doesn't tell you why it's there. But the cool thing that it does allow for is that other scientists across the community can use our study now to try to correlate with their own research. These soils, these buried profiles represent periods of stabilities, which may have some implications for our climatologists on the Front Range, who can now come and use our research as a source of information. So with that, thank you. I believe we have time.